Welcome to my channel. I'm here to explain two things. One, limitations of graphical method. Two, solving linear programming problem using graphical method. And this problem is of minimization type. Coming to the first question, limitations. First limitation is too many constraints is a problem. If you can notice in this question, you have two constraints. One, two. Even in the previous problem, which is of maximization type, you have only two constraints. So when you have more than two constraints, there is another method in linear programming problem using which the solution can be attained. Second limitation is two variables. Graphical method is applicable to only two variables. When you have third variable, you have another method in linear programming problem. These are the two limitations of graphical method. Now, coming to the other part of the question, solve linear programming problem by graphical method. This problem is of minimization type. Earlier, the previous problem is of maximization type. The difference is in minimization problem, you have greater than or equal to symbol, and also there are other differences which you will notice while solving the problem. Now, you have been given objective function, you have been given two constraints, you have been given non-negative restriction. So you have been given three things, and a linear programming problem has three things, which is nothing but objective function, constraints, non-negative restriction. Now, in order to attain this objective, minimizing z, we need to first take the we need to first take out the first equation. So from the first equation, substitute x is equal to 0 in this equation. You get y is equal to 30 by 5, which is nothing but 6. Similarly, now in the very same equation, for the very same equation, you have to substitute y is equal to 0. You get x is equal to 30 by 2, which is nothing but 15. Now the same process which you have followed for this equation have to be applied for the another equation. Now for this equation, substitute x is equal to 0. You get y is equal to 45 by 3, which is nothing but 15. Now substitute y is equal to 0 this time. You get x is equal to 45 by 6, which is nothing but 7.5. So the next step in this solving this problem is, once you have identified these points, the next thing is you need to substitute them. You need to plot them on the graph. So the points have been plotted on the graph. This plotting of the points on the graph helps us to identify the intersection point. This is the intersection point. So this line represents the first equation. This line represents the second equation. These two lines have helped us in identifying the intersection point. Now, this intersection point helps us to identify the feasible region. In minimization type problems, the upper boundary is considered. This upper boundary is nothing but the uh, feasible region. In So this region has 3 points: A, B, C. Now, in order to identify the let's say uh, minimum value, these 3 points have to be substituted in this equation. A, B, C values have to be substituted in this equation. So after substituting these points in this equation, after substituting these 3 points in this equation, you get, for A you get 300, for B you get 131.25, for C you get 150. Now look at the question. The question talks about minimum Z. It's asking us to uh, find out the minimum value. So out of these three values, the minimum value is 131.25. So this is the required answer. Now we can conclude that the manufacturer can attain the objective of minimizing the cost by producing approximately 6 quantities of X and approximately 4 quantities of Y.